Welcome to the Deep Dive. We're the show that digs into a pile of sources to pull out those surprising insights, the aha moments you need to really know what's going on. Today, we are plunging into the unseen engineering that's, well, everywhere around us. The invisible dance of energy we call heat transfer. It's definitely not just about setting your thermostat. It's, the fundamental force shaping everything, from how your morning coffee cools down to how spacecrafts actually survive out there in space.
Indeed. And our mission today really is to demystify this. It can seem complex. We'll pull out the crucial insights from the sources we've got, clarify the main principles, and spotlight those surprising details that make understanding heat transfer genuinely valuable for you. Think of it as maybe a shortcut to appreciating this hidden ballet of energy in our world.
Okay, let's start with the most intuitive way heat moves, conduction. This is heat transfer through direct contact. Like, imagine touching a hot pan, that immediate heat you feel. That's conduction, molecules just bumping against each other.
Precisely. And the bedrock principle here is Fourier's law of heat conduction. What's really crucial to get is that this isn't just some formula on a page. It's the fundamental reason your coffee cools down, or why heat always tries to balance out, even across the vacuum of space. Always moving from hot to cold.
Always hot to cold.
Always. And this law, it applies to all matter, solid, liquid, or gas. Heat flows in the direction of decreasing temperature. And if you picture temperature like contour lines on a map, heat flows straight downhill, perpendicular to those lines, those isotherms. Oh, and it's important to remember, this law came from experiments. It wasn't, derived from pure theory.
Okay, so if that's the law telling us how heat flows, then thermal conductivity, that's G or K, right?
Right.
Tells us how well a material lets heat pass through, sort of like its own speed limit for heat.
Exactly right. K is a material's basic ability to conduct heat. Our sources give some fascinating general ranges. For solids, pure metals, they can be anywhere from, say, 10 up to 400 watts per meter Kelvin.
Kilograms per meter Kelvin. Okay.
Yeah, it basically tells you how many watts of heat can flow through a 1 meter chunk for every 1 degree temperature difference. Higher number, heat, superhighway.
Got it.
Alloys are usually lower, maybe 10 to 120. Insulators, they're way down, 0.023 to maybe 2.9 WMK. Liquids, they're in a pretty tight range, 0.2 to 0.5. And gases are even lower conductors, 0.006 up to 0.5 WMK.
Wow, that is a huge difference.
Yeah.
Can you give us a couple of specific examples just to really nail down how massive that range is?
Sure. Think about silver, one of the best. It's around 410 WMK.
410. Okay.
Copper's right up there too, 385. Then you jump down to something like steel, maybe 40 WMK.
Big drop.
Huge. Now compare that to stuff meant to stop heat. Sawdust, 0.07. Glass wool, 0.03.
Tiny number.
Really tiny. And freon gas, way down at 0.0083. That just shows this enormous spectrum, right? And why picking the right material is absolutely key in engineering.
Hold on. So K isn't just fixed. You're saying its value can actually change depending on how you make the material or even just its temperature. That sounds, well, not what I expected. Why is that?
It absolutely changes, and yeah, it is fascinating. Several things affect K, especially in solids. First, chemical composition. Pure metals, really high K. But add even tiny impurities or mix it into an alloy, and K plummets.
Really?
Yeah, get this. Pure copper is 385 WMK. Pure nickel is 93. Mix them into monometal, 70% copper, 30% nickel, and it drops to just 24.
24. Wow.
Or add just a trace of arsenic to copper and its K falls to 142. It's like adding just a bit of grit to a smooth pipe. It messes up the flow dramatically.
So tiny atomic changes have these massive effects on heat flow.
Okay.
What else changes K?
Second, mechanical forming. Things like forging, drawing, bending, even heat treatment. They change the material's internal structure, its crystal lattice, and that affects K. Hardened steel, for example, has a lower K than annealed steel because its structure is, well, less orderly for heat to flow through easily.
Okay, thanks.
Third is temperature rise. Now, for most metals, K actually decreases as temperature goes up.
Decreases?
Yeah.
Why?
Because the atoms are vibrating more vigorously, right? And those vibrations actually get in the way. They hinder the movement of the free electrons that carry most of the heat in metals.
Interesting.
But for non-metallic solids like ceramics or insulators, K generally increases with temperature. Those vibrations start to help transfer energy more effectively.
Okay, so beyond just conductivity, are there other concepts that help us grasp how heat moves through materials?
Yes, there's thermal diffusivity. We use the Greek letter alpha, Isaac. It's defined as K divided by density times specific heat C. So I'll call K 1.
Okay, K over rho C. What does that tell us?
It's really significant. A higher alpha means heat diffuses or spreads faster through a material. Its temperature will change more quickly. It's super important for understanding unsteady heat transfer, like how fast does this thing heat up or cool down?
That raises a good point. Does heat always travel the same way through a material, regardless of direction? Or are there materials where direction actually matters?
Yeah, good question. That brings us to isotropic versus anisotropic materials. Most materials are isotropic. Their thermal properties are the same, whichever way you measure.
Like a block of metal.
Pretty much. But anisotropic materials, they behave differently depending on the direction. Wood is the classic example our source gives.
Wood. How so?
Its thermal conductivity can be way different along the grain compared to across the grain. Heat flows much more easily with the grain. It's like it has its own heat highway lanes.
Ah, okay. That's crucial for building, I guess.
Absolutely. From house frames to furniture, understanding that grain is important.
So, okay, conduction is heat moving through one thing. What happens when it hits a boundary or has to go through multiple layers? That's where we start thinking about resistance,
Yeah,
right? And how heat moves in more complex situations.
exactly. When we're calculating heat flow through different shapes or, say, multiple layers, we often use the idea of thermal resistance, Roth. It basically measures how much a material opposes heat flow, just like electrical resistance opposes current. It's used a lot for 1D conduction. Think flat walls, hollow pipes, hollow spheres. It simplifies the math, lets engineers quickly figure things out.
Right. But what if you have like a wall with insulation and siding,
Mm-hmm.
or heat conducting through metal, then convecting away into the air? Do you have to track each step separately?
Well, you could, but thankfully there's a shortcut. That's the overall heat transfer coefficient, usually called U.
Yeah.
U simplifies things for these composite structures. It bundles all the thermal resistances together, conduction through the solids, convection off the surfaces into one single value. Makes it way easier to figure out the total heat transfer from, say, inside a building to the outside air. Very handy for engineers.
Okay, that makes sense. Now,
Yeah.
prepare me for something weird. We always think adding insulation is good, right? Always reduces heat loss. But I've heard that's not always the case for, like, pipes, which just sounds wrong.
It is one of those really counterintuitive things. It's called the critical thickness of insulation. And you're right, for curved surfaces, cylinders and spheres, adding insulation doesn't always cut down heat loss, at least not initially.
Wait, really? Adding insulation increases heat loss? How?
Okay, what's fascinating here is that up to a certain critical radius, adding that insulation actually increases the outer surface area. If the convection off that larger surface area is strong enough, it can actually pull more heat away than the insulation is saving, especially if the convection coefficient H is low to begin with. But once you get beyond that critical radius, then adding more insulation works like you'd expect. It does reduce heat loss. There are formulas for it. For a cylinder, the critical radius RC is KH. For a sphere, it's RC equals 2KH. K is the insulation's conductivity, H the convection coefficient outside.
And 2K, okay.
But here's the crucial contrast. For a flat, plain wall, like your house wall, the critical thickness is 0. Any insulation you add always helps.
So if you're insulating a hot pipe, you could actually put on too little insulation and make things worse.
Potentially, yes. If you're below that critical radius, it's incredible.
Mind blown. Okay, and what if the heat isn't just flowing through the material, but is being generated inside it, like in electronics or something?
Right. That brings us to heat conduction with internal heat generation. This is when heat is actually produced within the material itself. Think about, your phone's battery getting warm, or the filament in an old light bulb, or maybe a nuclear fuel rod. We usually talk about volumetric heat generation, QG, in watts per cubic meter. Tells you how much heat pops up per unit volume. Sometimes, though, you might see it as Will-Am-Moore if they're assuming a standard thickness.
All right, we've covered heat moving through solids pretty well. But what about when fluids, air, water, whatever get involved? That sounds like where the action really picks up. That's convection, right?
Yeah, exactly. Convection is heat transfer that involves the movement of a fluid, liquid, or gas over a solid surface. It's driven by temperature differences. Crucially, unlike conduction's molecule-to-molecule transfer, convection relies on the bulk movement of the fluid itself carrying the heat.
Okay, and how do engineers usually categorize these flows? Seems like there could be a lot of different ways fluids can move heat.
Yeah, they're usually classified in a couple of main ways. First, based on what's driving the movement, you've got natural convection. That's purely driven by buoyancy warmer, less dense fluid rising.
Yeah.
Think of shimmering air above hot pavement or a hot air balloon.
Right.
Then there's forced convection. Here, something external makes the fluid move: a fan blowing on your computer chip, a pump circulating coolant in your car engine.
Makes sense.
And sometimes you get mixed convection, a bit of both happening. The second way is based on the geometry. Is it external flow, like wind blowing over a building, or internal flow, like water flowing inside a pipe?
Okay. These fluid interactions sound incredibly complex, though.
Mm-hmm.
How do engineers actually predict how much heat will transfer? Or compare different setups? It feels like you'd need some tools. This is where those dimensionless numbers come in, isn't it?
Absolutely. These numbers are indispensable. They boil down complex physics into single values that tell you what's dominating the process. First up, the Nusselt number, nu, defined as Ax-K fluid. It's basically the ratio of heat transfer by convection to what you'd get by pure conduction through that fluid if it just sat still.
So it tells you how much better convection is than just letting the fluid sit there.
Exactly. It shows the enhancement due to fluid motion. Now, this often gets confused with the Biot number.
Ah, yeah. How are they different?
Good question. The Biot number, BXXK solid, uses the thermal conductivity of the solid, base solid. It tells you if the solid's internal temperature stays fairly uniform during heat transfer. Nusselt number, nu x K fluid, uses the fluid's thermal conductivity, K fluid. It tells you about the heat transfer from the surface into the fluid, different focus.
Okay, got it. Solids' internal gradients versus fluids' surface transfer. Makes sense. What other key numbers are there?
We also have the Prandtl number, PR. That's NIA, the ratio of momentum diffusivity, kinematic viscosity, to thermal diffusivity.
Momentum diffusivity, like how fast flowiness spreads versus how fast heat spreads.
That's a great way to put it, yeah. It tells you the relative thickness of the velocity boundary layer versus the thermal boundary layer. High PR means momentum effects spread further than heat effects.
Okay.
Then there's the famous Reynolds number, RIX. It's the ratio of inertia forces to viscous forces. This is the big one for predicting flow regimes. Is it going to be smooth, orderly laminar flow, viscosity wins, or chaotic, swirling, turbulent flow, inertia wins?
Right, laminar versus turbulent.
And the trigger point, the critical Reynolds number, depends on the situation. About 500,000 for flow over a flat plate, but only around 2,000 for flow inside a round pipe before it starts getting turbulent.
Wow, much lower in a pipe.
Yeah, and for free convection, we use the Grashof number, GR, ratio of buoyancy to viscous forces, and the Rayleigh number, RA, which is just Grashof times Prandtl, combining buoyancy and diffusion effects.
Phew, okay. Lots of numbers. Is there any way to simplify the link between how the fluid flows and how much heat it transfers?
Well, there's the Reynolds analogy. It points out a strong connection between the velocity boundary layer and the thermal boundary layer.
Yeah.
Especially when the Prandtl number is close to 1, which it is for many gases.
And what does that let you do?
It basically allows engineers to estimate the convection heat transfer coefficient if they know the fluid friction, the drag. If you know how much drag there is, you can get a pretty good idea of the heat transfer.
Okay, that's useful. So boiling it all down for practical stuff. Which type of convection moves more heat generally?
Oh, definitely forced convection. For similar conditions, forced convection gives you much higher heat transfer coefficients than free or natural convection.
Makes sense. Like a fan cools you off way faster than just sitting still.
Exactly that. That external push makes a huge difference in how vigorously the fluid scrubs heat away from the surface.
Okay, let's shift gears again. What happens when materials actually change state? Like water turning to steam or vice versa? That seems like it would involve a lot of energy transfer.
It does, and it's incredibly efficient. We call it boiling heat transfer, when a liquid turns to vapor at a solid-liquid interface because of heat coming from the solid, the big advantage. Those vapor bubbles create a huge amount of agitation, stirring the liquid intensely. This leads to very large convection coefficients and really high heat transfer rates, even with just small temperature differences.
That's why boiling water heats things so fast.
Precisely. It's key for cooking, power generation, all sorts of things.
And boiling isn't just one thing, right? It happens in stages.
Yes, as you keep increasing the surface temperature compared to the liquid's boiling point, you go through distinct regimes. First, free convection boiling. Not much vapor yet, heat's just moving by natural convection in the liquid. Then the onset of nucleate boiling, ONB. The first tiny, stable bubbles start forming at specific spots on the surface.
Okay.
Then you hit nucleate boiling. This is the really vigorous part. Lots of bubbles forming rapidly all over the surface. Heat transfer shoots way up, Bubbles might be separate, or they might merge into columns or slugs of vapor.
That sounds intense.
It is, but then you can reach a limit called the critical heat flux, CHF. This is the absolute maximum heat flux you can get in nucleate boiling. For water at sea level, it's about 1 megawatt per square meter. That's a lot of energy, like 1,000 hairdryers focus on 1 square meter.
Whoa. And what happens if you try to push past that?
That's where you hit burnout. It's dangerous. A stable, continuous film of vapor forms right on the heating surface. Vapor is a terrible conductor, so it acts like an insulator. Heat transfer plummets, and the surface temperature can skyrocket very quickly, often melting or damaging the heater.
Yikes. Okay, avoid burnout. What about the reverse? Vapor turning back to liquid. Is that just boiling in reverse?
That's condensation heat transfer. It happens when you cool a vapor below its saturation temperature. And no, it's not quite just reverse boiling. How the liquid forms on the cool surface really matters. There are 2 main types. Film-wise condensation, where the liquid, the condensate, forms a continuous film covering the surface.
Like fog on a cold window.
Kind of, yeah. And then there's drop-wise condensation. Here, the condensate forms distinct, separate droplets. Large parts of the cool surface remain directly exposed to the vapor between the drops.
Okay, so which one transfers heat better? I'm guessing drop-wise, because the vapor can touch more of the cold surface directly.
You nailed it. Drop-wise condensation gives you a significantly higher heat transfer rate. That liquid film in film-wise condensation acts as a resistance barrier. With drop-wise, the vapor has much better access to the cold surface. So, practically speaking, engineers try to promote drop-wise condensation whenever they can. It usually happens on surfaces that repel water, like oily or specially coated surfaces.
Interesting. So we've got conduction, convection, phase change. Now let's tie these together in devices we see all the time. Heat exchangers. Things like radiators, AC coils.
Exactly. Heat exchangers are fundamental devices designed to transfer heat efficiently between 2 fluids without letting them mix. They often use lots of plates or tubes, sometimes with fins, all packed together to get a huge surface area for that heat exchange to happen across. Designing them is a real balancing act, maximizing transfer, minimizing pressure drop, cost, size.
And what's a major headache for these things? Something that can really degrade their performance over time.
Oh, the big one is fouling. It's a massive issue. Fouling is just the buildup of unwanted gunk on the heat transfer surfaces.
Gunk like what?
It can be lots of things. Scaling, that's mineral deposits like limescale from hard water. Corrosion fouling, basically rust or other oxide layers. Chemical reaction fouling, where stuff in the fluid reacts and deposits, like think burnt food on a pan. There's also freezing fouling, if something in the fluid solidifies, like wax. Biological fouling, algae, slime, even barnacles in seawater systems, and particulate fouling, just tiny particles settling out.
Wow, okay. Lots of ways for them to get clogged up.
Yep. And any of that fouling adds an extra layer of thermal resistance, making the heat exchanger less effective. Cleaning them can be a major maintenance cost.
So with all these complexities, how do engineers actually measure how well a heat exchanger is doing its job?
There are a few key metrics. One really common one is the logarithmic mean temperature difference, LMTD.
Logarithmic mean.
Why
logarithm?
Because the temperature difference between the 2 fluids usually changes as they flow through the exchanger. One gets colder, the other gets hotter. LMTD gives you the proper average temperature difference that's actually driving the heat transfer across the whole thing. A simple average doesn't work.
Okay. LMTD for the driving force. What else?
We also use effectiveness and the number of transfer units, NTU. These are dimensionless parameters. Effectiveness basically tells you how much heat the exchanger actually transferred compared to the maximum possible heat it could have transferred, theoretically. NTU is sort of a measure of the heat transfer size of the exchanger. They're really useful for design and analysis, especially when you don't know the outlet temperatures beforehand.
All right. And shifting gears slightly, what about those devices that seem almost magical at moving heat, the sort of superconductors of heat?
Ah, you must mean heat pipes. They are truly remarkable, designed for incredibly high rates of heat flow.
How high are we talking?
Well, their effective thermal conductance can be hundreds of times higher, maybe up to 500 times, than solid copper, one of the best metal conductors.
500 times better than copper.
Wow. They use phase change brilliantly. Inside a sealed pipe, there's a working fluid. Heat at one end makes the fluid evaporate, absorbing a huge amount of latent heat of vaporization. That vapor then travels very quickly, almost at the speed of sound sometimes, to the colder end of the pipe. There, it condenses back into liquid, releasing all that latent heat. Then, a wick structure, like a mesh or grooves, pulls the liquid back to the hot end via capillary action.
So it's a continuous cycle, just passively moving massive amounts of heat using evaporation and condensation.
Exactly. Incredibly efficient and often completely passive. They're used in everything from cooling electronics to managing heat on spacecraft.
That is genuinely amazing. Okay, finally, let's touch on the last major mode, radiation, the one that can travel through empty space. Truly a dance of photons.
That's right. Radiation is energy transfer via electromagnetic waves, or photons. The key thing, the huge difference from conduction and convection, is that radiation needs no medium. It can travel straight through a vacuum.
Which is why we feel the sun's heat, even though there's empty space between us.
Precisely. It's the only way heat can cross a vacuum. Absolutely vital for understanding solar energy, space tech, even just how things cool down at night by radiating heat to the cold sky.
And what's the fundamental law governing how much energy something radiates?
That's the Stefan Boltzmann law. It says the total energy emitted from a perfect radiator, what we call a black body, is directly proportional to the fourth power of its absolute temperature. The equation is Abe equals tau. That T to the fourth power is huge. Double the absolute temperature, you get 16 times the radiation.
Wow. T to the fourth.
Yeah.
And you stress absolute temperature.
Absolutely critical. Always use Kelvin or Rankine in radiation calculations. Using Celsius or Fahrenheit will give you completely wrong answers.
Got it. Kelvin only. Now, how do real objects compare to this ideal black body? Nothing's perfect, right?
Correct. Real surfaces have properties that describe how they interact with radiation. Emissivity tells you how well a real surface emits energy compared to a black body at the same temperature. It's a fraction between 0 and 1.
So 1 is a perfect emitter, 0 is none.
Exactly. Then there's absorptivity, the fraction of incoming radiation the surface absorbs, reflectivity, the fraction it reflects, and transmissivity, the fraction that passes straight through. These always have to add up. Go plus up 1. For most solid objects we deal with, they're opaque, so transmissivity is 0. In that case, go plus deps 1, 1. What's not reflected must be absorbed.
Okay. Absorptivity, reflectivity, emissivity.
And there's a crucial link, Kirchhoff's law. It states that for a surface that's in thermal equilibrium with its surroundings, its absorptivity equals its emissivity.
Alpha equals epsilon. Why is that important?
It's huge for things like designing solar collectors. You want a surface that absorbs the sun's radiation really well, high alpha, because the sun is super hot. But you don't want it to radiate its own heat away efficiently once it gets warm, so you want low emissivity at the collector's operating temperature. NASA actually developed special coatings, like black chrome, based on this principle. They're great at soaking up solar energy, but bad at re-radiating it. Very clever.
That is clever. Selective surfaces. Now, how does temperature affect the kind of radiation, like the color of light emitted? Why do things glow red, then white as they get hotter?
That's Wien's displacement law. It tells us that the wavelength where a black body emits its peak radiation is inversely proportional to its absolute temperature. Omax T equals constant.
So hotter means shorter wavelength.
Exactly. As things get hotter, the peak emission shifts from invisible infrared to red, then orange, yellow, white, and eventually even bluish for extremely hot objects. It's how we can tell the temperature of stars just by their color.
Fascinating. Okay, in a real situation with multiple surfaces radiating to each other, how do we figure out how much energy goes from surface A to surface B? It must depend on their shapes, how they face each other.
Absolutely. For that, we use view factors, sometimes called shape factors or configuration factors, usually written as phi. Phi is simply the fraction of the total radiation leaving surface I that directly hits surface J.
That's the fraction that makes it directly there.
Right. And they follow some key rules that help us calculate them. The summation rule. For any surface I in an enclosure, the sum of all view factors from I to all other surfaces J, including itself if I is concave, must equal 1. All the energy has to go somewhere. The reciprocity rule. AI phi j equals AJ FJI. It relates the view factor from I J to the one from J to I using their areas. Very useful. And the associative rule. If surface J is made of parts K and L, then phi K plus L, phi goes plus phi L. Radiation to the whole is the sum of radiation to the parts. These rules let us figure out complex radiation exchange.
Can you give a quick example or two of how view factors work?
Sure. A concave surface, like the inside of a bowl, it can see itself, so phi I is greater than 0. Radiation leaving one part can hit another part of the same bowl.
Okay.
2 concentric spheres. All the radiation leaving the inner sphere must hit the outer sphere, so inner outer equals 1. 2 large, infinite parallel plates facing each other. They only see each other, basically. F12 equals 1. A hemisphere sitting on a flat plane. Half the radiation leaving the hemisphere goes down to the plane. Hemisphere plane equals 0.5. These geometric ideas are key for designing furnaces, spacecraft thermal control, etc.
Makes sense. And
Wow.
finally, how do we block unwanted radiation? Like keeping cryogenic liquids super cold or making sure a thermometer isn't affected by a hot wall nearby.
For that, we use radiation shields. Their whole purpose is to drastically cut down the radiative heat transfer between two surfaces. They work by having very low emissivity and high reflectivity. They don't really remove heat, they just reflect most of the incoming radiation, effectively putting up a highly reflective barrier that increases the resistance to radiation flow.
What are they usually made of?
Often, they're thin sheets of plastic coated with highly reflective metal films like aluminum or gold on both sides. Think of those shiny emergency blankets. They're absolutely essential for insulating things like tanks of liquid nitrogen or oxygen, and also for shielding temperature sensors to make sure they read the actual air temperature, not the temperature of some hot or cold surface radiating nearby.
So let's try and wrap this up. We've journeyed through, wow, the tiny world of conduction, the fluid flows of convection, the powerful state changes in boiling and condensation, and even radiation's photon dance across vacuums.
Yeah.
It really is remarkable how these fundamental ideas govern so much of our everyday world and the tech around us. It's like invisible engineering holding everything together.
Absolutely. And understanding these details, these nuances, it isn't just academic. It really gives you a deeper appreciation for the energy flows that, design our homes, power our cars, keep our food from spoiling, even let us explore space. It really drives home how interconnected it all is. From just putting a lid on a pot to save energy, right up to designing a massive power plant. These aren't just abstract ideas, they're the rules energy follows.
Yeah, think about something as common as a refrigerator. Every single principle we talked about is working in there right now. Conduction through the walls, convection moving the cold air, even radiation between the food and the cold surfaces,
Right.
all silently working away. So how might understanding these principles maybe spark an idea for you? Or just let you appreciate that hidden dance of energy that's happening all around us all the time? What's one thing you'll maybe look at differently now, knowing the invisible forces pulling